So hello, everybody, and welcome to this webinar put on by the Connecticut IEEE Power Electronics Society. So for those of you who don't know me, my name is John Noon. I'm a senior electrical engineer at Otis Elevator Company and chair of the Connecticut PELS chapter. On behalf of the Connecticut PELS chapter, I'd like to sincerely thank you for joining the webinar presented by Ken Wyatt about PC board design and layout for low EMI power conversion. Before we kick off the webinar, I'd like to give you a short introduction to PELS for those of you who may not be familiar. PELS is a society within the IEEE, which is the largest technical professional society. PELS's vision statement is to be the global resource that all people turn to for education, knowledge sharing, technical events, and networking in the power electronics field. PELS's core purpose is to foster power electronics technological innovation and excellence for the benefit of humanity. Benefits of IEEE membership include online access to all PELS-sponsored conference proceedings, including APEC and ECCE papers, as well as the listed journals. Personally, I think this is a huge benefit. Beyond access to technical papers, there are also many avenues to get involved, focus on either technical development or more people-focused roles. Both are excellent for professional development, depending on what you want to get out of it. Personally, I'm involved in both by serving as a reviewer for APEC and ECCE for the past few years, as well as more recently as a reviewer for both the transactions on power electronics and the transactions on industry applications. Again, personally, I think it's important for people in industry to be involved in these functions in order to offer our perspective, as well as to kind of force ourselves to stay up to date on the latest technology trends. All of the different tracks and resources are available on the PELS website. So for example, when you're at APEC or ECCE, you could spend a little bit of time going to the IEEE Society meetings and see all the different groups, such as technical committees, membership, really everything are looking for volunteers. So you should be able to align your interests with an opportunity to give back to our profession. To provide some more detail and context on the Connecticut chapter, we have the same or similar goals as the national organization, but focused on Connecticut engineers. So part of that is through in-person events, but some of that goal is also by broadening our horizons by reaching out into the broader community and engaging nationwide, such as through webinars like today, where we're fortunate to have Ken, who's presenting remotely all the way from Colorado. So you can see a few of, on the next page, you can see a few of the events that we've had so far. So as I mentioned, we're a new chapter and hosted our kickoff event about a year ago, last October. We've had a variety of events, from in-person technical lectures to social events, factory tours, and webinars, all to try and best serve our members. I'd like to take a minute to highlight the upcoming New England Power Electronics Symposium, which is happening at UConn in about 2 weeks. This is a great new event started by Professor Ali Bazi at UConn with the high-quality lineup of speakers over 2 days. The Connecticut PELS chapter is hosting a roundtable on Thursday evening after the Wolf Speed workshop. But there's a great workshop on Thursday, as well as a very strong lineup on Friday as well. And this is put on in partnership with the student branch chapter at UConn, as well as the new Connecticut Power Electronics Center of Excellence. So in conclusion, PELS is volunteer driven and about you, the members, or soon to be members. Spoiler is that all events will be open to both IEEE and non-IEEE members. We want to make sure that we're not interested in gatekeeping any knowledge or networking opportunities, but I hope that everybody can see the benefits of membership. So if you're interested, you can use one of the code on the screen to get a complimentary PELS membership if you're already an IEEE member. So I'd like to thank and highlight all the Connecticut PELS XCOM members who make events like this possible, as well as all the chapters that we've collaborated with on the event today. So Eastern North Carolina, Atlanta, Long Island, UConn, Boston, Virginia Tech, City College of New York, Princeton, Philly, Central Jersey, as well as the Binghamton chapter. So thank you all for your help and support. So with that, I would like to take a minute to introduce you to our speaker today. So Ken Wyatt is the principal consultant of Wyatt Technical Services and has served 3 years as the senior technical editor for Interface Technology magazine from 2016 through 2018. He's worked in the field of EMC engineering for over 30 years with a specialty in EMI troubleshooting and pre-compliance testing. He is a co-author of the popular EMC Pocket Guide and RFI radio interference Pocket Guide. He's also co-authored the book with Patrick Andre, EMI Troubleshooting Cookbook for Product Designers, with the foreword by Henry Ott. He recently completed and released a 3-volume EMC troubleshooting trilogy, which is now available through Amazon. He's widely published and published a monthly column for the Signal Integrity Journal, has blogged for EDN.com for many years, has a monthly column, EMC Bench Notes for In Compliance Magazine, writes regularly for EE World, and continues to write for Interface Technology Magazine. Ken's a senior life member of the IEEE and a longtime member of the EMC Society. So with that, I would like to thank you again, Ken, for your presentation today, and to turn it over to you. Thank you.
Well, thanks so much, John. Am I sharing my screen okay?
I don't see it yet.
Okay, well, I mean, I have to reshare, I guess. There we go.
Okay, so yep, I can see it now.
Yep. Okay, there we go. Well, thanks so much, John, and the Connecticut PELS Society for the invitation to speak. I really appreciate it. And thanks so much for that nice introduction. Yes, I've been in the industry quite some time and learned a lot. Currently, I've been consulting for about 16 years. Spent most of my career with Hewlett Packard and Agilent Technologies. And anyway, it's been a fun ride. Today, I'd like to talk about uh, some of the things that I've noticed in client projects that I've worked on through the years, and in particular, designing and layout for low EMI power conversion, and primarily we'll be focusing on the smaller DC to DC converters, which are so prevalent on circuit boards today. But I have had a chance to work on some large power conversion projects. I thought I'd throw this picture in. I blanked out the company names, but when you can crawl half of your body inside a power conversion system, you know, you're talking about some big power. But back to DC converters, they've really become a dominant EMI source and cause both radiated and conducted emissions. And in particular, these onboard DC to DC converters tend to contaminate sensitive sensors and cellular communications and other wireless technologies. And it's primarily from the rise and fall time, as I'm sure most of you already know. But I've seen broadband EMI all the way up to about 2 gigahertz. And so we're going to show you some examples of that. Let's see, I need to there we go. So why do these switch mode power converters suck for EMI? These new DC to DC converters are usually nowadays switching between 1 to 3 megahertz, and they have very fast rise and fall times, and that's what creates the harmonic content. I'll show you some examples that I've measured this broadband EMI all the way out to 1.5 gigahertz. And this energy tends to couple to cables and even within your board through capacitive or inductive coupling. As power levels are increasing, one example would be artificial intelligence requires really high currents and power levels. And so it's causing it's requiring larger components, but basically what I'm going to cover today, while it's focused on at the circuit board level, can be applied to larger systems. And I just want to make sure that that is clear. The basic layout and rules of physics apply no matter what kind of power conversion circuit you're using. Yeah. So let's just look at a simple DC to DC buck converter. On the left, you've got a loop, a current loop between the input capacitance and the switches. On the right, you have a current loop um, through the inductor and the output capacitor. And as these switches S1 and S2 switch alternately, you get a continual current flowing in the primary side. We call that the hot loop sometimes. And we want to make sure actually both these loop areas are minimized. And you can see an example of that in the figure, the circuit board on the right. Here's an example of offline isolated flyback, and the flyback converters have two hot loops. And again, you want the input and output capacitors and the switches, the switch devices, to be as close together as possible to reduce the loop area. So here's an example of a DC to DC converter layout. In this case, the input and output loops are pretty tight, and I also like to see that the input and output circuitry are as isolated apart as possible, so we don't get capacitive or inductive coupling between output and input. This layout, this is from an LT 8074, one of the Linear's silent switch micromodule, which I'll talk about in a little bit. But this particular module, DC to DC converter, includes the input and output capacitors within the package, which makes layout a whole lot easier. This layout that is in the data sheet for this component assumes an adjacent solid return plane underneath, although it's not shown. And I have a note here, never mount associated switching components, for example, the inductor on the opposite side of the board from the main circuitry. That's important so that we avoid fast edge switching currents going from the top to the bottom of the board repeatedly. I had a client put the inductor, the switch inductor, on the bottom side of the board, and all the other circuitry was on the top side. And the result was broadband interference all the way up through GPS band, around 1574 megahertz. And it was so bad that the GPS could not lock onto the satellites at all. Another thing to watch for when laying out your PC board is we want to avoid overlapping the input planes or traces with the output planes or traces, because this, as you can see in the schematic on the right, this creates a parasitic capacitance that couples the switched input from the VBAT, say the primary DC coming in, which is going to be really noisy. We don't want that coupling to the output. And one way I do this when I'm evaluating boards is I'll color in the primary circuitry in one color and the secondary circuitry and the ground return in a different color, so I can immediately see that that there might be an issue. In a similar fashion, we want, when we're laying out filter, the noise filters, we want to minimize the parasitic coupling between input of the filter and the output. And I've tried to depict that here. And you can see, if you look at the common mode choke, that is actually used as both a differential mode filter and a common mode filter. And I've tried to group the components between the two. For example, the X capacitor there works with the differential mode inductance of that common mode choke, and then the common mode, the Y capacitors on the right side work with the common mode inductance to act as a filter. But we don't want to mix the input of the X capacitor with the Y capacitor side. Just what I really like to see is that these power line filters are laid out in a linear fashion, just like you'd lay it out on a schematic. That way you minimize any couplings, especially if you're using a dual section filter where you have two common mode chokes. You want to be careful not to create coupling, especially between the two chokes. So one of the things that I specialize in is benchtop characterization of EMI. And so we're going to show you some ways that I characterize DC to DC converters. Pictured here is a wireless wildlife camera board that hunters or wildlife experts like to use. You bolt this to a tree and you can monitor wildlife. But you can see in this example, the DC to DC converter is located right next to the cellular module. The manufacturer of that cellular module recommends doing that, but when you do that, you risk coupling the noise right into the cellular antenna or input to that module. And in this case, it was so noisy it could not acquire the cell towers. So we'll talk about what I call partitioning of circuitry, where you identify the known high energy sources and the more sensitive source of more sensitive receiving sources, and you try and separate those. And I can measure that with a simple probe. I don't know if you can see this in my in my picture, but I use a small loop probe, and I can probe different points on the circuit boards and help identify the noisiest parts. It turns out that DC to DC converters, many of them have ringing, and so that's something you can see on the oscilloscope. And in the upper picture, you can see, maybe a typical switching waveform. But you can see once you expand that leading edge, there is a ring frequency there. And in this case, it's 172 megahertz ring. And what's interesting is that ringing can create a harmonic in the frequency spectrum. And I'll show you that here in a moment. I've got a video demo of power supply ringing on my website, which is, I'll show you on the last page, I think, is emc-seminars.com. But here's a blow up of that rising edge. It's about a half a nanosecond rising edge, and it's going to create quite a lot of emissions. I've developed a method that I call non-invasive probing of DC to DC converters, and the problem is when you're using a scope probe, the risk is shorting something with that probe, and so you can take an H field loop probe basically and couple that to the switch inductor, which I have diagrammed here. And it turns out that the output voltage is proportional to the voltage across the inductor, and that voltage across the inductor is what we're interested in. Here's an example with using an oscilloscope probe on the bottom and a near field probe at the top. All the interesting EMC characteristics are identical between the two probes. And these beehive probes that I like to use are pretty high bandwidth. The medium one that I showed you a few minutes ago has a bandwidth over a gigahertz. And so you're not going to lose rise time information, for example. So this is just to demonstrate that the near field probe coupled to the inductor is a valid measurement technique and a whole lot safer. So here's what happens. This is from Clayton Paul's book. So you have this ring frequency, and it translates from the time domain to the frequency domain as a wide peak in the emission spectrum. And here I am measuring some ringing on a gallium nitride a DC to DC converter. And it's switching at, I believe, 1 megahertz. And you can see the ring there on the screen. Here it is blown up better. So we have the time domain ringing on the left and the resulting frequency domain plot on the right. And you can see the ring frequency is 217 megahertz. And you can see it peaking up in the aqua and violet traces where I have the arrow pointing. But you can also, interestingly, see the second harmonic of that ring frequency around, well, it's 434 megahertz. And then there's other peaks higher in frequency that I'm not showing. But you know, this ring frequency, we're looking out to a gigahertz on the right-hand plot. You can see that broadband noise is extending out to around 600 or 700 megahertz. So what I'm going to do in this last half of the talk, I'm going to give you 10 tips for reducing switch mode power converter EMI. And the first tip is PC board layout and stack up. I find that my clients that are successful use the proper stack up, and the clients that are not successful, at least the first time around, are not using the correct stack up or the optimal stack up. And it really is key to your design. If you get the circuit board and stack up layout wrong, you've added a lot of risk. So there's a couple main rules to follow. And that is every signal trace needs an adjacent solid return plane or trace. And every power trace or plane needs an adjacent return path, either a plane or a trace. So that's really the key factor. Because we want to, the signals are actually, which I'll explain in a moment, the signals are actually electromagnetic waves, and that electromagnetic wave needs to be trapped between the circuit trace and return plane. But number three, this also includes return paths up and down through layers. So if you're going from the top to the bottom layer, for example, we need a continuous path to trap that electromagnetic wave, and we use stitching vias or stitching capacitors to do that. But following these rules will dictate what the stack-up should be. And I've got a series of articles in EDM magazine on some details on how to do that and the physics of signal propagation. So here's something to keep in mind. Something to keep in mind is at low frequencies, the return path is going to be fairly wide from source to load and back. As you increase frequency, that return path tends to follow directly under the signal trace. And so the break point is right around 50 to 100 kilohertz. Anything over 100 kilohertz, that return path is going to be right under the trace. And you can use that or capitalize on that physics by partitioning, basically separating noisy parts from quiet parts of your circuit. So circuit traces are actually waveguides. Keep that in mind as we go through the points here. So continuing with tip one, I want to explain the circuits versus fields point of view. The circuit's point of view is probably what we all learned in undergrad, college, and it was at least implied that that signals were really the flow of electrons in copper traces, and that's not true at all. But what is true is that from a circuit's point of view, all signal currents must return back to their source. And if you don't control that return path very well, you're going to, that's just going to lead to EMI issues. Now, the field's point of view, signal and power transients propagate as electromagnetic fields, and these fields travel in the dielectric space at near light speed within within the dielectric space, and they induce this electronic wave or electromagnetic wave induces conduction and displacement currents, which are the ones that flow back to the source. Now, the speed of these conduction and displacement currents is very slow because electron flow is quite slow. Basically, the drift velocity of electrons is you can look it up on Wikipedia, but it's actually much less than 1 millimeter per second because the electrons are bound pretty tightly within the copper molecules. So bottom line is the signal energy is in the fields and not the copper. It's not due to the flow of electrons. So here's maybe a little better diagram. It's a cross section of a signal trace and a return plane. And as the wave propagates from left to right within the dielectric space, the conduction current in red and the displacement current in blue those currents will return back to the source, but at a very slow rate. While the electromagnetic wave, of course, in FR4, it's about half of light speed, or about 6 inches per nanosecond in FR4 material. So what that means is because we want to keep the electromagnetic wave trapped at all times between the circuit trace and the return plane, that really dictates our circuit board design. And here's a diagram of a very typical 4-layer board with signal and ground return on the top 2 layers and a power plane and signals on the bottom 2 layers. And there's a couple problems with this. You can use this stack up successfully, but the risk is really high for EMI, and it depends, the clock speeds and so forth. As you for just simple circuits, this is probably adequate, but for dense designs, high performance, fast clocks, you're probably not going to meet EMC regulations with this stack up. And the problem is the bottom 2 layers, signals are referenced to the power plane, which will trap that electromagnetic wave okay, but how is that, how are the return currents going to return back to the source, which is probably on the top side of the board? And so it really requires a lot of decoupling capacitors to couple that return plane and the power plane together tightly. The other problem is ideally we want the power and ground return planes very close together. And on a 62 mil standard thickness board, the power plane and ground planes are too far apart. They're 30 to 40 mils apart, and so you don't get the best coupling that way either. And there's a couple ways to get around this, and that is to use 2 ground reference planes in the middle layers with signals and routed power on the top and bottom, and that's a successful way to design your stack up. Some really high sensitive wireless designs reverse those layers so that the ground reference planes are on the top and bottom layers and the signals are in inner layers. So that's and there's a number of other ways of doing it as well. For 6-layer boards, the typical 6-layer board stack up on the left has a lot of the same problems as the 4-layer. If you look at the two bottom layers, the signal layer there is reference to the power plane, and the power and the return planes are spaced way too far apart. But even more importantly, any power transients are going to be referenced to the return plane on layer 2, and those power transients are going to couple to the two inner signal layers. So you got to get noisy power on the two signal layers. On the right-hand side is one of many ways around that. You can put the power and return plane in the middle layers and use a ground return plane and signals and routed power on the top and bottom two layers. So that's one way around that. The idea is we want a solid return plane for every signal layer. So you could go signal, return plane signal, okay, which is, if you do that throughout your stack up, that would work too. So here's a scenario where we have two planes. We need to go from top to bottom of the board, and the if both the planes are return planes, you just simply stitch them together at the via where the signal propagates through. But the problem lies, of course, if the planes are different potentials. So if one is a reference plane or return plane and the other is a voltage plane, then you need to use a stitching capacitor placed near the via. As far as power distribution networks, we're still on tip 1, by the way, but we'll go quicker through the other tips. But I really want to focus on the layout and the stack up concepts. So let's start on the right-hand side of this picture. You're familiar with the fact that some switching devices have on-chip capacitors, and then we have decoupling capacitors and bulk capacitors. So these capacitors are really energy storage devices. And when the switch device switches, it's going to call for energy from the on-chip capacitors, if there are any. And the larger processors sometimes have on-chip capacitors. And then when those on-chip capacitors, now moving right to left, when those on-chip capacitors are depleted, they're going to signal for the decoupling capacitor to replenish their energy. The decoupling capacitor stores energy, and when it depletes, then it calls on the bulk capacitor. And so we want the power distribution network to be as low impedance as possible. And I see some designs putting ferrite beads in line with the power distribution network. And the reason I don't like to see impedances added is because it's going to affect the performance of these energy storage capacitors. So keep that in mind when you're laying out power distribution. As far as how to mount decoupling capacitors, this is a slide from Bruce Archambault. Basically, we don't want in the lower right, we don't want to route long traces connecting these decoupling capacitors. And so I wanted to show you, the good, bad, and ugly. Um, the connections to each end of the decoupling capacitor should be uh, very, very short trace lengths. And the top three examples are what Bruce thinks is a good layout. You do have to be cautious about wicking solder into the via away from the component. So that's maybe one thing to think about. I mentioned the concept of partitioning earlier, where we want to separate out known noisy functions from quiet circuitry. And so this is just one concept drawing where we have on the right-hand side all our I/O connectors and power input, and all the filtering is right next to those connectors. And if we have Ethernet or USB or one of those kind of technologies, that circuitry should be located near the I/O as well, so we don't run Ethernet clocks all over the board. All the digital circuitry is generally grouped together, but we want it, as far separated from anything wireless or sensitive sensors or analog circuitry, for example. We'd like some separation there. And as far as the power conversion goes, that is usually distributed around as needed, but again, we want to make sure that the broadband EMI from those power conversion circuits are located far away from any sensitive circuitry. Okay, let's move on to the other 10 tips. So when we're specifying DC to DC converters, we want to specify low EMI converters. And the IC manufacturers are finally getting a clue that most of the early days of DC to DC converter designs were pretty noisy. And so both TI and Analog Devices have developed quieter EMI DC to DC converters. So that's one thing. And some of these have optional spread spectrum, which can be useful. Some of the newer packages include, as I mentioned earlier, the input and output capacitors are mounted inside the package. And so your loop areas are as small as they can be, and that's great. The silent switcher 2 on the right-hand side not only has the input and output capacitors inside, but it also has the switching inductor inside. Now you can, tip 3, we want to keep everything on the same layer. It doesn't matter if it's the top or bottom, but if you have a bunch of sensitive analog circuitry, you might, or wireless or RF circuitry, you might think about putting all the power conversion on the bottom side. But we do want to keep it all on the same layer and group together, and as I mentioned earlier. Okay, so we think we've already covered this. So tip 4 is we want the input and output capacitors as located as close as possible to the switch node itself, and that goes also for the switch inductor. Tip 5, a ground return plane must be solid, and we did get some questions on from some power conversion designers as to whether the plane must be solid under the switch node or under the switch inductor. There are exceptions. If you're using a common mode filter in a DC application like automotive or military, um, the advice would be to remove the return plane under that common mode choke, so that it doesn't um, effectively the parasitic capacitance doesn't effectively short out that common mode choke. So there are exceptions. Another exception might be certain EMs, certain Ethernet connectors. Um, it's best to remove the ground or the return plane just underneath that connector. But I think those are the two main exceptions. Otherwise, we want to keep the return plane solid, because if we're running a high frequency signal trace across a gap, you can see the result on the right-hand plot of the frequency spectrum, and we're looking up to as high as a gigahertz. In red is the EMI of a trace over a gap. And if we're running that same trace over a solid return, that's in blue, and you can see there's quite a difference. There's a 10 to 20 dB difference in the level of EMI if you run a high-speed trace over a gap, and that's just one gap. Some of the circuit boards I evaluate have multiple gaps, so you can imagine the EMI that can be generated. And I do have an interesting video on my website that demonstrates this principle. So we got some questions on whether to put a void under the switch inductor or the switch node of a DC to DC converter, or voids under both. And Steve Sandler and I co-authored an article for Signal Integrity Journal where we did a study. He had 4 different boards built. In the blue on the lower right, the upper left board has a solid plane, and then we have voids under different combinations of the switch node and the inductor. There's some concern whether, capacitive parasitic capacitance would affect the performance of the inductor. And in the plots on the at the top, the solid return plane was in blue, and then the other different colored lines are different different configurations. And overall, it looked like the solid plane was best, except that there's always some exceptions. But even in the middle plot there, it's mostly better than not. But the differences are slight. So it made a bigger difference in differential mode noise. Not so much difference in common mode in the center there and the left. So anyway, we tried to answer that question. I think what I would recommend is using a solid plane. Tip 6, we want to use shielded inductors. And basically, if you can see the windings, it is not shielded. And my colleague Patrick DeRoy, while he was at CST, did some simulations on that, and you can see the simulation in the lower right. But yeah, so use a shielded inductor. And this is, again, a difference between shielded and unshielded as far as the EMI. Unshielded is in the blue, shielded is in the red. And you can see as you increase in frequency, there's more and more of a difference. Okay, here's a tip that I never realized until I took a course from Rick Hartley, and that is you can orient the output inductor for low EMI. Inductors have a start on the winding and an end on the winding, and the start is usually covered by several turns of wire before it gets to the end. And so if you position or locate the pin 1 of the inductor towards the switch node, the switching side of the inductor tends to get somewhat shielded by the secondary by the additional turns, and so you get less EMI on the right side of the inductor as the left side, and it Rick says that it'll reduce EMI by 2 to 3 dB. So sometimes we want all the reduction we can get. So tip 8, use local shields. And this is mainly useful for wireless technology if you have that on your board, or high sensitive analog circuitry or audio circuitry. You may need to use local shields. And most of these shields are effective mainly for E fields. So we know we get a high E field at the switch node of DC to DC converters. So you may, especially for sensitive circuitry, you may need to put a local shield over the power conversion, the block, for example. Here's a difference again from Patrick DeRoy. He tacked in a copper shield, as you can see in the upper right, and that was over the switch inductor and switch node. And in red is without the shield, green is with the shield for either E field on the left or H field on the right. And you'll see that a local shield will shield H fields, but just not as good as it does for E fields. Now, tip 9, use of RF absorber. This is something I've been experimenting with. And again, it's most useful for applications where you might have some wireless technology or sensitive analog or sensor signals where the broadband, either digital switching noise or the broadband signals from power conversion are coupling in to your sensitive analog or sensor circuitry, or coupling in to the receiver section of your wireless modules. This material, it's a ferrite loaded, usually silicon based, sometimes material with an adhesive on one side, and it is insulated, so you can stick that material over traces or over the body of an IC, or flex cables, for example, to absorb the electromagnetic field. And Worth has an application note on a couple of them on this material. I had amassed a whole collection of this flexible absorber, which I characterized in the frequency domain. And so I'm starting to use that now. Here's a couple of sample plots that were actually used on a wireless body-worn product. And you can see I'm plotting up to 3.2 gigahertz, and it really starts to become effective in the 400 to 500 megahertz range, and it just gets better with frequency. But I used that. This was a body-worn device that I had a hand in, and there's a video camera on it, and let's see, the video flex cable is I put a patch over the video flex cable. That's the rightmost patch there with the X. I put one on the DDR RAM package, and the small one was placed over the power management IC, the PMIC. And here's the results. In this case, we were concerned with the cellular reception. And you can see in the upper right, there's a strong video signal or video harmonic, along with some narrowband harmonics that are a little bit hard to see in that picture. But I have markers on each one of them. And so the before was in the upper right, the after is in the lower right, and that video coupling was reduced by at least 15 dB. It's basically the signal is in the noise floor, and all the narrowband harmonics are gone. And it made the difference between passing the cellular receive sensitivity test and not. And you can see I'm in the lower left, I'm sensing that signal with a small antenna. And that's how I got the frequency response on the upper right. But just a few patches made the difference. Tip 10, we want to route any attached or internally routed cables away from power conversion circuitry and any kind of digital processing. And this really applies for any kind of circuit. Doesn't matter if it's wireless or not. For example, I was working on a security robot that is designed to roll around on factory or warehouse floors, and it has various sensors on it, camera, smoke, gas sensors, and they had routed all the motor control and power cables along with the sensor cables along one side. So we rerouted the cables, all the sensitive cables on one side of the robot and the power cables on the other, and that solved their problem. Oh, look, there's a tip 11. This is a bonus tip, and that is don't trust manufacturers' data sheets. Some are okay, some are not. And I've got a couple examples here from TI, but it's not just TI. All the semiconductor manufacturers will give you bad information as far as layout. There's on the left, we've got the switch node. You can see the switch node. It's on the left side of the IC in the middle. And that switch node goes from the top side to the bottom side of the board, and it's fairly long. It's a long trace. And we want to, in fact, that switch node extends all the way to the inductor, the bottom side of the inductor on the left. And so basically we've got the switch node flowing all over the circuit board, top side and bottom side. And we're switching, if it's a 12-volt circuit down to 3 volts, we're switching, 9 volts up and down and with very fast edges. So that's just basically a poor layout. In addition, the input and output capacitors, which are you'll see on the left side, share a common ground return path, and those capacitors should drop straight down to a solid plane underneath on the second layer. Now on the right side, the switch node is small enough, so that's not a problem. But I've circled an area where it's even more egregious, where the input and output capacitors are sharing the same ground path. Basically, they're in other words, they're two coupled together. Remember, I like to see a power conversion circuit laid out linearly, where you've got power coming in on one side and power exiting on the other side of all the circuitry. And here we've coupled the input to the output as close as we could get together. So that's going to be a noisy layout. Never use single point grounds as current returns. That's just you're just asking to couple noise from one place to another when you do that. So wrapping up, I've got some suggested references. The top bullet is my series of articles on designing PC boards for low EMI. And then if you want to read about EMI absorber, that ferrite absorber material, that's in the second bullet. And then I've got a couple articles on just how I characterize DC to DC converters with near field probes, and then the co-authored study with Steve Sandler is on there too. So I think that wraps things up. You can see here my various blogs. I'm currently writing for 4 different publications. But this year I've got a monthly article in in Compliance magazine called EMC Bench Notes, and that basically, if you're not familiar with EMC measurements and troubleshooting, that's a series that started in January and is concluding this month, or it'll conclude in December. So I'd recommend that. And then anybody who's needing to do EMC troubleshooting, the worst place you can do that is at the third-party test lab. The best place to do that is right on your own workbench. And so during the pandemic, I had a chance to write some books on how to get your company some level of EMC troubleshooting ability. And then volume 2 and 3 cover emissions and immunity testing that you can do right on your workbench. So with that, I will conclude. And John, what's the best way to handle questions and answers?
I was going to read them out loud from the chat if that works for you.
Oh yeah, okay, sure.
So thank you very much for the great presentation. I really appreciate your time, and thank you again. So I sent it to the chat, but as a reminder, please type any questions in the chat and I'll read them aloud. So I will share a PDF of the presentation as well as a link to the recording with all registered attendees within a week of the event. So there's already a few great questions in the chat. So
okay, let's
maybe if we can have take like five minutes or so. So for the first one, it says regarding the H field probe, where to place it on the inductor, because the H field probe is an air core inductor and weakly coupled to the inductor. The placement of the probe is critical.
So, of what most onboard inductors are wound that way, but just holding it flat picks up the best. And again, I didn't explain the math on that one slide, but it really doesn't matter what the mutual coupling factor is, as long as you get a readable signal on your oscilloscope.
Okay. Thank you. For the next question, do any of the reduced EMI tips have the potential to cause reduced signal integrity?
Yeah, so there's definitely a connection between signal integrity and EMI, and generally so long as you when you fix EMI, you usually fix signal integrity at the same time, especially in board layout and routing. For best signal integrity, if it's single-ended, you definitely want a solid return plane. If it's differential, it's not as necessary. Um, if you're going from balanced to unbalanced, you need to a little hard to explain, but that would be an example would be Ethernet, where you're going from pseudo differential mode out to the connector to a true differential mode through the transformer. And so that's one consideration. The other big consideration for signal integrity, well, I guess it'd be more power integrity, would be to make sure your power distribution networks are as low impedance as possible. But there's definitely a connection, and usually if you improve one, you'll improve the other two as well.
Thank you. So regarding local shields, do you have a recommended material for wireless systems, like a
Well,
shield
yeah,
material?
good. A good question. It depends why you're using the shield, and most of the time when I'm using a shield, it's to shield E fields, which are generated by fast switching voltages, like from the switch node of a power converter. Um, if I'm getting strong magnetic fields, then um, what works best for E fields isn't necessarily best for H fields. Especially, well, you also have to consider the frequency. For low frequency magnetic fields, you're kind of forced into using things like steel or mu metal. For high frequency magnetic fields, almost any kind of metal is going to work out. Um, Let me go back to that where we're looking at this slide here, where so he's using in this case a thin copper, and of course that blocks E fields really well. H fields not so well, but it does block them a good probably over 10 dB. Yeah, but over 10 dB, so which is significant. E fields are being blocked by 25 dB in this example. Most of the local shield manufacturers, they use thin aluminum or tin-plated steel, maybe.
Okay, okay, thank you. Um, so how important is splitting the signal ground and power ground? It looks like a big ground plane is sufficient since the high frequency noise signals will navigate themselves.
Um, I would not split power and signal ground. Now there's cases where you're using if you're using a the yeah, let me go back to that slide. If you are using the yeah, here if you're using the flyback or isolated flyback, then I would say, yeah, the left side would be power return. I try not to use the word ground because it means so much to people, so many different definitions. So on the left of this would be the power return, and because it's isolated, on the right side would be my digital return. Um, Now, there's cases where you use something similar to isolate patient circuitry using an isolated or an isolator. And so on the primary side of an isolator, you could call it one ground or one return, and on the right side a different return. But you want to make sure not to mix um, those planes. But yeah, great question. Generally speaking, to answer your question, I would just use a solid return under everything, except showing in this picture the common mode choke on the input. I would probably void out the return plane underneath it so it doesn't the parasitic capacitance doesn't effectively short it out at higher frequencies.
That was a excellent last comment that answered the next question. So somebody
Okay.
asked about cutouts under the common mode choke, and so that was
Yeah.
a good segue.
Well, and there's a lot of companies that use this kind of a filter uh, for their power input, whether it's AC or DC input. This is used a lot in medical and military or automotive and military applications. So yeah, uh,
And there's two final questions, if that's okay with you.
sure.
Um, so one is which EDI tools have the highest fidelity predicting and simulating PCB EMI? Um, and then the second one is there a current limitation for using RF absorbing material?
Okay, I can answer that last one. That's one reason why I wanted to characterize all the samples I had received over the years, is to figure out exactly what the absorbency was versus frequency. And most of the flexible absorbers are become effective in the hundreds of megahertz and higher. In fact, most of them were designed for the gigahertz frequencies. They just happen to work okay in the upper hundreds of megahertz. Now the first part of that question, I didn't quite understand. What's EDI?
So I would say like which I don't know EDI either, but maybe like which simulation tools are your favorite for
Oh, oh, okay.
EMI?
Yeah, another good question. I don't use simulators at all, except for filter design. Um, and I think I'm not sure exactly how deep that question was posed, but uh, when you have a some electronic gadget, um, there are so many variables that you need to consider, plus all the parasitics that may not even be known to really come up with an accurate simulation of a product. Now you can simulate things like interconnects or circuit traces, um, very limited models basically. I know companies are trying to, in fact, for 15 or 20 years, they've been trying to predict the radiated and conducted EMI from uh, a complex product. And I don't think anybody's really been that successful yet. Now there are software packages that are rule based. So um, the rule checkers that companies like IBM originally came out with, and other companies, those are nice for when you're laying out the circuit board, but for just predicting the EMC performance of a product using a simulator, that you're probably not going to be successful. Now there's a company EDA that uses simulation for aircraft, and like lightning simulations and antenna placement simulations. That's a valid simulation, but that's also a very limited model. You've got the aircraft body, and you've got an antenna of a certain length and location, and you can simulate couplings from the antenna to maybe other antennas and that kind of thing. That's a valid simulation, but to simulate the performance of a product for EMC, I don't think we're there yet. I'm not sure we'll ever get there. So most of my techniques are bench level, as you can, if you take a look at the articles that I write, it's all tests and characterizations that you can do right on the workbench to predict performance. A couple of my articles were on pre-compliance testing, for example, where you can set up your own pre-compliance test for radiated emissions and some of the cautions. But so I think that's the extent of it, and you'll see you can do an awful lot on the workbench prior to getting your compliance testing done. And that's the reason I wrote the books, that my troubleshooting trilogy books. So I hope that's a help to people.
Well, thank you again for your great presentation, for taking the time today.
Well,
So
thanks for hosting.
yes, thank you again. So with
Thanks.
that, as a reminder, I'll send out the slides and the recording to everybody. So thank you again, everybody who was able to attend today, and thank you especially again, Ken, for your time.
And thanks to all the listeners.
Have a great rest of your day.
Don't take care.